ready, they can go to the recording to be able to see the notes. Okay, so let's get started. So in chapter 7.1, let's kind of just recap what we learned in chapter 7.1. So in chapter 7.1, we learn about confidence interval. And we learn about confidence interval for the population proportion. So we kind of learn if I don't know the population proportion, I could use the estimate, which we call the point of estimate, which in this case will p hat, to estimate what the population proportion could be. So that's what we learned in 7.1. So 7.2, oops, should say 2. We're going to be doing confidence interval. But we're going to be doing confidence interval for the population mean. So for mu. But in this case scenario, we're not going to know what mu is, but we're going to be using X bar to estimate what mu could be. So that's what we're going to be working on today. So we're going to be working on finding the confidence interval for mu. And we're going to be doing that when sigma is unknown. So when sigma is unknown, that means we don't know. That means we don't know the population proportion, or the population standard deviation. So what we're going to do, we're going to use the sample standard deviation to estimate that. So anytime we're using sample standard deviation, that means instead of using the t distribution, the z distribution, which we have been using, we're going to be using now the t distribution. So today we're going to be working with the t distribution, because for all of the problems that we're going to work on for today, we're going to have the sample standard deviation, not the population standard deviation. Questions so far?
No.
Let's see, got something in the chat. Nope. Perfect. All right, so let's get started. So I'm going to go over some property or some key important thing about the t distribution. All right, so for the t distribution, we usually use the t distribution when we have a sample standard deviation. So anytime you have sample standard deviation, you're always going to use the t distribution. So for the t distribution is dependent on the degree of freedom, because the degree of freedom is kind of telling us how accurate or how inaccurate the t value is going to be. Usually if you have a degree of freedom that's low, it's usually going to be pretty much inaccurate. If we have a degree of freedom which is high, usually that should be a little bit more accurate value. So the way that you find degrees of freedom is a very simple formula. So I'm going to put df for degrees of freedom. So the way that you find degrees of freedom is n minus 1. Cool. So anytime you want to find degrees of freedom is equal to n minus 1. So if I tell you the sample size is 20, degrees of freedom will be equal to 19, because you do n minus 1. You did 20 minus 1, which is 19. All right. So that's the first one. So let's go on down to the second one. So the second one is saying if we have the t value, for the t value, the mean should always be 0 and our data set should be symmetric. So we're saying if I know what t value is equal to, our mean should be 0. For the distribution of a t distribution, it should look fairly normally distributed. So it should look something like that. For the t-distribution, you just kind of know the area underneath the curve will always be 100%. And if I were to cut this area into two equal area, one side of it will be 50%, the other side will be 50%. So assuming if I cut it down the middle, half of the data set should be to the left of it, half of the data set should be to the right of it. So that's what this one is saying for part C. It is saying the area under the curve should be equal to 1 or 100%. And if you cut it in half, half of the data set should be on one half, the other half should be on the other half. Any question in regard to that so far? All right. So you kind of realize for the t-distribution is a little bit more robust. So when we say robust, what you mean is a little bit more forgiving than the z-distribution. Because for the z-distribution, since I have the population standard deviation, we kind of know like how far away it's possible to go before something has become a little bit too like unlikely to occur. But for the t-distribution, since we're not using the population standard deviation, since we're using the sample standard deviation, it's actually able to go a little bit further away from the middle because pretty much we're using a sample standard deviation, which is not going to be as accurate as a population standard deviation. So if you look at E, that's what E is talking about. It's saying the area in the tail of the t-distribution is a little bit greater than the area in the tail of the standard normal distribution because we're using S as an estimate of sigma, thereby introducing further variability into the t statistic. All right. And for the last one, it just said as the sample size n increases, the density curve of a t get closer to the standard normal density curve. The result occur because the sample size n increases the value of S get closer to the value of sigma by the law of large number. So if you kind of remember the law of large number, it said the bigger your sample size get, the closer and closer it should be getting to the mean, but also it should be getting closer and closer to the population standard deviation. So if we have a sample size says like of 1 million, our sample standard deviation and our population standard deviation should be pretty close to each other or not equal to the same value. All right, and that's it for the t-distribution. Any question in regard to the t-distribution? All right, and you kind of know for the t-distribution, it is possible to have a negative t-distribution and a positive t-value because, stop share. And you kind of remember for the t-distribution says the middle should be 0. That means the left of 0 should be negative value. And that means to the right of 0, you should have positive value. So you just know t value, it could be negative, but the t value, it could also be positive. All right, so let's go on down. All right, so just to kind of recap about the central limit theorem. So if you remember for the central limit theorem, n has to be greater than or equal to 30. If n is not greater than or equal to 30, then we say it's not normally distributed. So n has to be greater than or equal to 30. If n is like 10 or 15 and we don't know that the distribution is normal, then for that problem, we are not going to be able to do it. All right. So let's actually get to the formula and let's go over the key thing for the formula. All right, so the first thing, if you look at it, is the point of estimate. So if you look at this one, the point of estimate is changing because in section 7.1, the point of estimate was p hat. But now our point of estimate is going to be X bar because since I don't know what the population mean is, I'm trying to estimate what the population mean is. So the best estimate of the population mean will be the sample mean. So if I don't know what the population mean is, if I get a sample, the sample should be a good estimate on what it should be equal to. Up next, we're going to standard error. So for standard error, the symbol I put is SE. So for standard error, it is equal to sample standard deviation divided by square root of n. So anytime you want to find standard error, you get S divided by square root of n. Once you get the standard error, you want to get margin of error. To get margin of error, you do T alpha divided by 2, and you multiply that by standard deviation, or the standard error. And that will give us the margin of error. And then lastly, to get the confidence interval, sorry about that. This is going to be the final formula for the confidence interval, where you get the point of estimate, and we're going to add it, and we're going to subtract that to our margin of error. Everybody good with that? All right, so let's go ahead and let's do the very first problem. So for this one, it says a random sample 24 US cell phone user age 18 and older in May 2011 found that the average number of text messages sent or received per day is 41.5 message with a standard deviation of 167. So first thing we're gonna go ahead and do, we're gonna go ahead and just write down all of the information that's given to us. So the first thing that's given to us is the 24. So 24 is my n value. So we put 24 is equal to n. All right, so the second thing they give me, if you look at it, it said the average number. So it said the average number of text messages sent or received per day is 41.5. So that means X bar is equal to 41.5. And then they tell me it had the standard deviation. So telling me of the sample of 24, we got a standard deviation of 167. So we say S is 167. So far, any question in regard to how I got those three values? All right, so let's do part A. So for part A, it says state the population and parameter of interest. It says use the information from the sample to give the best estimate of the population parameter. All right, so right now we just want to list out like who are they sampling. So if you look at it, they're just sampling US cell phone user age 18 and older. So we'll say population is equal to US cell phone so that's my population. So pretty much it paid off if you don't remember well, not the formula, but the definition of population. Population is just pretty much who are they interested in or the characteristic that they're interested in. If you look at it, they're looking for the parameter. So the parameter that they're looking for is the average number of text message sent or receive per day. So that's the parameter. So that's the numerical value that we're trying to attain. We're trying to attain the average number of text messages sent or received per day. And lastly, the best estimate of the population parameter. So we kind of want to know the point of estimate. That's going to equal to our sample mean, which is equal to 41.5. Because since I don't know what the average number of text messages sent or received per day for the entire population, what we're going to do, we're going to get the estimate of what that could be, which is a sample mean. So the sample mean was 41.5. All right. Any question in regard to so far anything I have written down for part A? All right. So let's do part B. So for part B, it says find and interpret a 95%. So that should say confidence interval. It is a little typo. So it says a confidence interval for the mean number of text messages. All right, so let's go ahead and do that. So the first thing we're gonna go ahead and do, I'm gonna go ahead and find T alpha divided by 2. So in order for me to find T alpha divided by 2, I'm gonna need two things. I'm gonna need to know what the confidence level is, but I also need to know what the degree of freedom is. All right, so what's my confidence level for this problem? What did it tell us the confidence interval should be?
95%.
Yeah, 95%. So we'll put 95% here. What would be my degree of freedom if degree of freedom is equal to n minus 1?
20.
All right. So I know confidence level is equal to 95%. I know degree of freedom is equal to 23. Any questions so far? I got that? Okay, so this is where the T table, you're gonna need it. So if you have your T table, okay. So the T table is gonna be a little bit different because I don't want the Z value anymore. I want the T value. So to find the T value, we have to look for degrees of freedom, but you also have to look for the confidence level. So if you look at the confidence level, here's my confidence level. Less than 95%. Now what you have to do, you have to look for degrees of freedom. So degrees of freedom, you're looking for 23. So that's here. So if you look at where do they intercept, they intercept in that number. So that's our T value. So the T value will be 2.069. All right. So we get 20, well, not 20, but 2.069. Any question? I got the 2.069. All right. So up next, we're gonna go ahead and do, I'm gonna go ahead and do standard error. So to find standard error is equal to S divided by square root of N. S in this case scenario, we said was equal to 167. divided by square root of n, where n is equal to 24. So I'm actually going to do that in my calculator just to kind of save a little bit of time. So I'm going to do 167 divided by square root of 24. If you do that in your calculator, you should get 34 point, what do you say, 0.1. If you did it on your calculator, you should have gotten like 34.0887. But to kind of make this easier, we're going to round it up to one decimal place. So we'll get 34.1. Any question for standard error? Okay, up next we're going to get margin of error. So to get margin of error, you get T alpha divided by 2, multiply that by standard error. So T is equal to 2.069 multiplied by standard error, which we just found to be 34.1. So we get 2.069 multiplied by 34.1. Any question where the 2.069 or the 34.1 come from? Okay, so I'm going to go ahead and multiply those two out. So I'll just do that in my calculator. So we'll do 2.069 multiplied by 34.1. And we get roughly margin of error is 70.6. So where I get the 30, so yeah, so the 34.1 is just doing basic math, just doing this. You just have to do 167 divided by square root of 24. So if you do that in your calculator, where you do 167 divided by radical 24, that's where the 34.1 come from. All right. So far we got standard error. We just found margin of error. Any question in regard to how I found margin of error? Okay, so the last part, what we're gonna do, we're gonna get margin of error and add it and subtract it to my point of estimate. Our point of estimate in this case is 41.5. So we'll say, oops, they say 41.5 plus or minus my margin of error, which is 70.6. All right, so just remember, this is telling me that you're gonna do the operation twice. So that means you have to subtract them and then add them. So they say 41.5 minus 70.6. All right, so we get negative 29.1. So negative 29.1. Then we do this exactly the same thing, but we change it to addition. And you get 112.1. So our confidence interval is what I have on my note. So let me switch over to my notes, so that way you can see how I wrote down the confidence interval. So if you look at it, I get negative 29.1 all the way to 112.1. And that's your confidence interval. All right. Any question on how I found that those two numbers? All right, so I'm gonna show you how to double check your answer by using either ClassCalc or by using the TI-83. So let me show you how to do it on the TI-83. All right, so if you have a TI-83, turn it on. So first thing you wanna do, you wanna hit the stats button. If you look right here with this test, you want to move it over there. So you want to use the right arrow and just move it all the way to test. Then you want to go down. And for this one, you want to use the T interval, which is number 8. So we use T interval. So you select it. For this one, since everything is given to us, you want to use the stats button. So you make sure stats is selected. You go down, you put the mean. So the mean in this case was 41.5. Oops, 5. If you look at the standard deviation is 167. If you look at my sample size, it was 24. And lastly, if you look at my confidence level, it was 95%. So 95%. Any questions so far how I got this? Or how I inputted it? Sweet. All right, so press enter. And if you look at it, we almost got exactly identical to what they got. So they got negative 29.01. We got negative 29.1. And then if you look at the upper bound, we got 112.02, which we got 112.1. So it's pretty close. Like the only reason why it's off because like we're rounding off stuff and the calculator is not rounding off anything. So that's why R is a little bit off, but that's okay. Any question on how to deal with the TI-84? All right, so I'm gonna show you how to deal with class calc now. So in class calc, you wanna make sure you're in graphing mode. Once you're in graphing mode, you press this, you go to stats, you go to tests, and now you're looking for something that says T interval. If you look at the third row, you wanna actually use the third row where it says T-INT. So that you stand for T interval. So if you look at it, it asks you for the mean. So the mean is blah, 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 41.5. If you look at the standard deviation, it's 167. If you look at the sample size is 24. And lastly, if you put confidence level is equal to 95%. For class calc, it does want you to enter it as a decimal. If you don't enter it as a decimal, it will give you a syntax error. All right. So if you actually look at our T interval, it gave us negative 29.0179 all the way to 112.017915. So identical to what the TI-84 gave us. So it doesn't really matter if you use the TI-83 or class calc, you should still get the same answer. All right. Any question in regard to class calc? All right, perfect. All right, so let me switch back to my notes. Notes. All right, so we found the confidence interval, but if you look at it, it says find and interpret a 95% confidence interval. So we already found this, and now we want to interpret it. So let's go ahead and interpret it. So for the interpretation, we'll say we are, and then you put the confidence level, 95% confident that the population mean, and then if you actually go back to part A should kind of help you out for this. Because we said that the parameter is the average number of text messages sent or received per day. So will you say that? So the population mean number of text messages received or cent per day. And then you put whatever the confidence interval is. Per day is between, let's see, negative 29.1 and 112. All right, and that's it for the interpretation. So if you kind of remember the interpretation we did for the population proportion, is pretty much the same thing. Instead of saying population proportion, we're saying population mean, but pretty much the same. All right, any question for this one? All right, so let's go on to this next one. So for this one says, for a simple random sample of 20 Honda Accord, the mean gas mileage was 23 miles per the gallon with a standard deviation of 1.5 miles per the gallon. So for this one said, what would be the best point of estimate for the population mean mile per the gallon for a 2005 Honda Accord? So that's asking for the point of estimate. So for the point of estimate, since I don't know what the population mean is, the best estimate for the population mean will be, well, will be X bar. And in this case, X bar is equal to 23 mile per the gallon. So that's it for A. So A pretty much just knowing the definition that point of estimate is the same thing as X bar if we're trying to calculate the population mean. Any question for A? All right, let's do B. So for B, it says find the margin of error for a 95% confidence level and explain what it represents. All right, so let's do B. So for B, we want to do the margin of error. So the margin of error, we're actually going to take this a little bit faster. So the margin of error is equal to T alpha divided by 2 multiplied by S divided by square root of N. So the first thing we're going to go ahead and do, we're going to go ahead and just find what is my T value equal to. So just remember T value, the same thing as saying the critical value. So to find T value, we're going to need two things. We're going to need to find out what the degree of freedom is. So we're going to need to find what the degree of freedom is. We're also going to need to find what the confidence level is equal to. So let's do the easy one. What's our confidence level?
95%.
Perfect. So 95%. What would be my degree of freedom?
$2.069.
Not my degree of freedom.
It's minus
Oh,
1.
sorry, I'm on the wrong one.
So what's my degree of freedom for this one?
19.
Yeah, 19. Okay, if you look at my sample size is 20. So N is equal to 20. So degree of freedom is equal to N minus 1, which you get 20 minus 1, give you 19. So yeah, so that's your degrees of freedom. Any question how I got degrees of freedom or confidence level? All right, so what I'm going to go ahead and do, I'm going to transition over to the T table. So the T table, I'm going to look for degrees of freedom and confidence level. All right, so confidence level is 95%. So once again, I'm using this column. But now what we want to do, we want to use a degrees of freedom of 19. So that's this row over here. So if you look at where the two lines intersect, they intersect at 2.093. All right. Everybody go on 2.093. 2.093. All right, so far I found 2.093. Up next, we're gonna get my S. S is the sample standard deviation. So if you actually read the passage in the beginning, it says for a simple random sample of 20 Honda Accord, the mean gas mileage was 23 miles per the gallon with a standard deviation of 1.5 miles per the gallon. So in this case, my mile per the gallon, or sorry, my standard deviation will just equal to 1.5. Any question on the 1.5?
No.
All right. So let's do n. If you look at the last thing, it says take the square root of n. So that means square root of 20. So we're going to do 2.093 multiplied by 1.5 divided by square root of 20. All right, so I'll do this in the TI-83, but you could do it with the with the class calc, you should get exactly the same answer. So you go 2.093 multiply by 1.5 divided by square root of 20. And if you calculate that, you get 0.702. Just to kind of make this easy, we'll just make it into 0.7. Everybody good with 0.7 for margin of error? All right, so the margin of error, you're kind of giving it the give and take. So telling you this is how much give we're gonna have for our point of estimate. Can we kind of know the point of estimate is not gonna be 100% correct, but the margin of error is telling us how far away can we be off and still be considered correct. So say if we actually found the population mean mile per gallon for 2005 Honda Accord, and we find it to be like 23.1, the confidence interval will still be correct because 23.1 is within 0.7 of our point of estimate. So that's what the margin of error is telling us. It's telling us how far away can we be off and still be considered correct. All right, and that's it for B. Any question in regard to B? All right, so let's do C. So for C, we want to construct a confidence interval. So let me take you back to the notes. All right, so we want to construct a confidence interval. So to construct a confidence interval, all you have to do is get the mean, add it, and subtract it to the margin of error. So in this case scenario, the mean is 23. You want to add it and subtract it to margin of error, which is 0.7. So if I do that, where you get 22.3, and we get 23.7. So our confidence interval telling us that the population mean mile per the gallon for a 2005 Honda Accord should be anywhere between 22.3 all the way to 23.7. And that's how you get the confidence interval. Any question in regard to the confidence interval? All right, so before we go and do the interpretation, I'm gonna go ahead and double check my answer by using ClassCalc and the TI-83. So that way you can see how ClassCalc and TI-83 should reinforce your answer. So TI-83 first. So for the TI-83, you're gonna hit the stats button. you're gonna go over here where it says tests, and we're gonna go over here where it says t-test or t-interval, sorry. Select the t-interval. So for the mean is 23. Our standard deviation was 1.5. Our sample size was 20. And our confidence interval was 95%, so we can just leave that as is. All right. So if you look at it, with the TI-84, we get 22.298, which if you use the 9 to round up the 2, you get 22.3. And then you get 23.702. So if you look at this answer and the answer that we got, is pretty close to the answer that we got. It is off because of rounding off error. All right, but that's how you deal with the TI-84. Any question for the TI-84? Okay, let's do class calc. Oops, stops here. All right, so let's do class calc. So let's re-enter everything. So we go to the stats button, we go to test, and you go to t-interval. So for x bar is equal to 23. For standard deviation of x, or just standard deviation, we get 1.5. For our sample size, we get 20. For confidence level, we get 0.95. Right. So if you look what the class calc gave us, 22.2979 and 23.702022, which is identical with the TI-84 gave us. So no matter if you have a TI-83 or 80 or a class calc, you should be able to get the answer. Any question in regards to that? All right, so let's go ahead and do the interpretation. So we'll say we are 95%, oops, forgot the percentage. Nope, that's not the percentage. So we are 95% confident that the population mean mile per the gallon for a 2005 Honda Accord is between 22.3 and 23.7. That'll be it for part C. Any question for part C? All right, let's do part D. So for part D, it says based on the confidence interval found in part C, is it likely that the mean gas mileage of a 2005 Honda Accord is 15? So we want to use the confidence interval that we got for part C. So in part C, we found the confidence interval to be anywhere between 22.3 and 23.7. So based off of that confidence interval, we want to see, is 15 likely to occur? So all you have to do is see, does it fall between these two numbers, or does it fall below this number or above this number? If it falls between those two numbers, then we say it is likely that 15 is the population mean gas mileage of a 2005 Honda Accord. But if 15 fall below the lowest bound or above the upper bound, then we say no, it's not likely. So for this one, what should we say, that is likely or that is unlikely? Yeah, so you want to say not likely. So you say, since 15 does not fall between 22.3 and 23.7. We will say right, so we'll say since 15 does not fall between 22.3 and 23.7, we will say that it is unlikely that the MPG of a 2005 Honda Accord is 15. And that's it for the second problem. Any question in regard to the second problem?
No.
All right, so let's move on down. All right, so for the next thing we're gonna get into how big of a sample size do we need depending on our margin, well, depending on how big of a margin of error do we want and our sample standard deviation. So if you kind of remember at the end of 7.1, we went over like how big of a sample size do we need if we're doing proportional data set. So we're gonna do exactly the same thing, but we're also gonna do this for the mean if we're trying to estimate what the mean is. So if we're trying to estimate what the mean is, what we're gonna use this formula that says you're gonna get the z value multiplied by sample standard deviation and then divided by margin of error. And once you get that, you're gonna square this. And just remember your n value should be rounded up to the nearest whole number. So this is saying if we have a margin of error and if we know the sample standard deviation, we could calculate how big of a sample size do we need depending on our confidence level. So if we want a big confidence level or a small confidence level, it will kind of dictate how big of a sample size we're gonna need. But that's the formula. Any question in regard to that formula? All right, so let's go ahead and do this first example. So it said a researcher wanted to determine the mean number of hours per week, Sunday through Saturday, the typical person watched television. Results from the Sullivan Statistics Survey indicate the sample standard deviation is 7.5. So all they're giving me here is the standard deviation. So they're telling us S is equal to 7.5. Everybody go with S is equal to 7.5. Perfect. So A says, how many people are needed to estimate the number of hours people watch television per week within 2 hours with a 95%? So that should say confidence, not condense. So let's go ahead and do this problem. So we already know S is equal to 7.5. You should also be able to get that confidence level is equal to 95%. And we're going to use this information in order to get our Z value. And then we want margin of error. So if you look at the margin of error, they tell us we want to be within 2 hours. So since we want to be within 2 hours, they're telling you that's our margin of error. Because if we want to be within 2 hours, that means it's a plus or minus 2 hours. So it could be +2 or -2. That's still the same thing. So they're telling us margin of error is equal to 2. So far we know margin of error is equal to 2. I know sample standard deviation is equal to 7.5. So the only thing we don't know is our Z value. Any question in regard to anything I have written so far?
No.
All right, so I'm gonna go ahead and find the Z value. So we're gonna use the T table. So for the T table, so remember for this one, we're looking for Z alpha divided by 2. So that means once again, we're using this row over here. So if you look at 95% is over here. So that means we're gonna use 1.96 for Z. So any question why we're using 1.96?
Why do we look for something like the other ones?
What was that again?
Like the other ones, we looked for like 19 and then why do
Well,
we? Okay.
well, for the problem, did they ever tell us the sample size?
No.
Because if you actually look at the problem, we're trying to find what the sample size is. So for the t value, you can't really use the t value because for the t value, you need to know how big of a sample size you have. So that way you can find the degrees of freedom. So since I don't know what the sample size is, that way we're going to use the z value.
Oh, okay.
Okay. Yeah, we're just looking for the z value, Elizabeth. All right. So we get z equal to 1.96. 1.96. 1.96. All right, so if you look at it, I already know my z value is 1.96. I know my margin of error is 2. I know my sample standard deviation is 7.5. Let's go ahead and enter this into the formula and we will be done with it. So we'll say n is equal to z, which is 1.96, multiply standard deviation, which is 7.5, divided by my margin of error, which is 2, and you want to take this to the second power. So I'm going to go over to Class Calc, and I'm going to go ahead and just do this calculation on Class Calc. So we'll say Class Calc, Class Calc. So if you look at me, you do parenthesis, 1.96 multiply by 7.5 divided by 2. If you want to get outside from the bottom, you want to hit this arrow to the right, and that way you're outside of it. And then you put to the second power, so I'm going to put a to this 2, and we're done. So you get 54.0225. So 54.0225. Any question? I got 54.0225.
So that's the sample size.
Correct, but that's still not the final answer.
Oh my God. Okay.
But you just have to do one little thing. It's nothing very complicated. All right, so if you look, we get 54.0225, but if you remember this little sentence right here, it says where n is rounded up to the nearest whole number. So you always have to round it up to the nearest whole number. So this will be 55, and that's your final answer. All right, but that's A. Any question in regard to A? All right, so let's do B. So if you look at B, once again, this should say confidence. All right, so it said how many people are needed to estimate the number of hours people watch television per week within 1 hour with a 95% confidence. So if you kind of look at it, everything is staying the same. What's the one thing that's actually changing?
1 hour. Margin of error.
Yeah, so my margin of error is changing from 2 hour to 1 hour. So I'm going to copy this, paste it, and you change that from a 2 to a 1. All right. So instead of putting margin of error of 2 hour, we're going to say margin of error of 1. So if you look at it, if we change it from a margin of error 2 to a margin of error 1, which one is more accurate, part A or part B?
B.
Yeah, so we want B to be more accurate. So what do you think is going to happen with the sample size? Do you think we're going to need more sample size, or do you think we're going to need less sample size?
More.
Yeah, because if you want to be more precise or more accurate, it's going to tell you need a bigger sample size. But let's go over and let's check that out, and let's do the math on, here, let's do it on the TI-84. So on the TI-84, we'll say, ooh, let me clear this. So we'll say parenthesis 1.96, oops, 6, multiply by 7.5, divided by 1. You close the parenthesis, and you put x to the second power. You press equal. And what do you know? We got a bigger value. So we got 216.09. So our final answer should be 217. All right, but that's your answer for part B. Any question for part B? All right, so lastly, let's do C. C is essentially just a reflection. So it said, what effect does doubling the required accuracy have on the sample size? So if you look at part A, we had it as 2 as our margin of error. And then we say we wanted to double the accuracy. So if we double the accuracy, we got 1. So when we double the accuracy, what happened to the sample size? Did it tell us we need a bigger sample size? Or did it tell us we need a smaller sample size?
Your sample size need to be bigger.
Yeah, we need to have a bigger sample size. So we'll say so yeah, so we'll say when we double the accuracy, we got that we needed a bigger sample size because when we went from a margin of error from 2 to 1, we saw that the margin of error of 1, we needed 217 as the sample size. But when we had a margin of error of 2 hours, we said we only needed a sample size of 55 people. So yeah, so doubling the accuracy will make it where your sample size has to be bigger. But that's it for C. Any question for C? All right, let's move on down. Okay. So what we just did, we did confidence interval for the mean. So we did confidence interval for the mean when sigma is unknown. So if sigma is unknown, that means we use the t distribution. So that's very important because right now what we're gonna do the confidence interval for the mean when sigma is known. So if we do know that sigma is known, the only thing that's gonna change instead of using the t distribution, we're gonna be using the z distribution. So here's the new formula on how to calculate the confidence interval when sigma is known. So if you kind of notice for standard error, we change it instead of saying sig s, we put sigma. And then for margin of error, nope. Instead of having the t distribution, we have the z distribution. So you have to just know if we know the standard deviation of the population, instead of using the t distribution, now we're gonna be using the z distribution. Any questions so far about that change on the formula? Okay.
And that's only when we don't know the margin of error.
Well, we don't know the population standard deviation.
Oh, okay.
If I don't know the population standard deviation, we use the t distribution. If I know the population standard deviation, we use the z distribution. So let's go ahead and use this problem. So for this one, it says people have died in boat and aircraft accident because a obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of the mean so that boat, aircraft, elevator, and other such devices do not become dangerously overloaded. Use the weight of men from a random sample. We obtain these sample statistics for a simple random sample of 40. So we have n is equal to 40, and we got a sample mean of 172.55 pounds. So it says research from several other sources suggests that the population of weight of men have a standard deviation given by sigma is equal to 26 pounds. So if you look at this one, they gave us sigma. So since we know sigma is equal to 26 pounds, we don't have to use a sample standard deviation. In this case, we're going to use the z distribution. So that's how you're going to know when to use the z distribution versus when to use the t distribution. If sigma is known to you, and usually they'll say population standard deviation, you use the z distribution. But if you have a sample standard deviation, that's when you want to use the t distribution. Any question in regard to that so far? All right. So let's do part A. So for part A, it says find the best point estimate of the mean weight of the population of all men. So for this one, we'll say X bar is equal to 172.55. All right, and that's it for A, because A, they just want the best point of estimate of the mean weight of a population of all men. Let's do part B. Part B says constructing 95% confidence interval estimate of the mean weight of all men. So if you look at it, we want to find a 95% confidence interval of the mean weight of all men. So first thing we're gonna go ahead and do, we're gonna go ahead and find z value. So that's z alpha divided by 2. So to find z alpha divided by 2, we're gonna go ahead and use the t table. So let me just transition over and find the t table. All right. So if you look at it, I already found it. It's right over here. We found it from before. Since we want a confidence level 95%, we'll just use 1.96. 1.96. All right, so 1.96, that will be my Z value. Up next, I'm gonna go ahead and get margin of error. So to get margin of error, you get Z alpha divided by 2 times sigma divided by square root of n. That's gonna give us Z alpha divided by 2, which is 1.96, multiplied by sigma, which is, oops, sorry about that, which is 26, all divided by square root of n, and in this case scenario, they told us it was 40. Any question where the 1.96 times 26 divided by square root of 40 come from? All right, so I'm gonna go ahead and work this out on my calculator. You could do this on ClassCalc or do it on your TI-84. It should give you exactly the same answer. So if I do this on my calculator, you should get approximately 8.1. If you did it on your calculator, you should have gone like 8.057. But I could use the 5 to round up the 0 to 1. So that way you're going to put 8.1. All right, so for the final step, we're going to do the confidence interval. So the confidence interval, we're going to get X bar, which is 172.55, plus or minus 8.1. So if I do 172.55 minus 8.1, you get 164.45. Now I'm going to do the operation again. I'm going to do 172.55 plus 8.1. And now you get 180.65. And that's your confidence interval for the population standard deviation. Any question in regard to the confidence interval for population standard deviation? Cool. All right, so I'm also going to show you how to do this with the TI-84 or ClassCalc. So the 172.55 is come from the problem, Edgar. So if you do, just look over here. It's right there. The 172.55. All right. So let's go over and let me show you how to do that with the TI-83 or 84. And then we'll do it with the ClassCalc. So for TI-84, you go to the stats button, you go where it says tests, and you want to go over there where it says number 7, Z interval. So instead of using the T interval, you use the Z interval. So one thing you should notice, if you look right here where it says sigma, instead of saying S, it's been replaced by sigma, and that's because you're using the Z interval. So for sigma, you want to put 26. For X bar, you're going to put 172.55. For N, you're going to put, I believe, was 40. Yeah, 40. Confidence level was 95%. Go to calculate, and if you look at it, it'll give us 164.49, and it give me 180.61. So if you look at it, we're slightly off. And the reason why we're slightly off, because we rounded off some of our number, versus with the calculator didn't round off any of the number. But if you look at it, it's pretty close to what we got. So that's how you deal with the TI-84. Any question for the TI-84? All right, so let's do ClassCalc. All right, so for ClassCalc, what you want to do, you go over here where it says stats, you go tests. Instead of doing the T interval, now we're doing the Z interval, which should be in the first row all the way at the end. So you put sigma is equal to 26. X bar is equal to 172.55. My sample size is 40, so you put 40. Lastly, my confidence level, we got it to be 95%, so put 0.95. And if you look at it, you get 164.492,665 and 180.607335. So if you look at it, we're pretty close to this answer. The only reason we're not spot on to the answer, like I said, because we rounded off some of the number. But that's it for that last problem. Any question for that last problem? All right, so let's do this. So let's do part C. So part C says, well, here, let me finish part C because I really can't go back all the way. So for part C, it says, what do the results suggest about the mean weight of 166.3 pounds that we use to determine the safe passenger capacity of water vessel in 1960 as given in the National Transportation and Safety Board safety recommendation? All right, so if you look at it, in 1960, they used this as the mean weight for men. So if I look at the confidence interval, is it possible that 166.3, that's still the population mean weight for men? You might want to check that again. So if you look at it, 164 is smaller than 166.3. So 163 does go in between it, but you might want to reconsider this because if you look at it, it barely got into this confidence interval. So they might want to readjust this population mean. So you might want to readjust this population mean because if you look at it, this might not be relevant for today average mean weight. So we'll say yes. Oops. Since 166.3 fall between 164.45 and 180.65. And that's it. So we'll say a yes since 166.3 fall between 164.45 and 180.65, but you might want to reconsider the 166 and get a more accurate for today time because that's probably not gonna last. All right. Any question for C? All right. What was your question about page 11? Like, what question was it? A, B, C, D? All right, yeah. So for part C, it says, what effect does doubling the required accuracy have on the sample size? So if you look at part A, we had a margin of error of 2. So that's our margin of error. So that's how accurate we want it to be. But in part B, we have a margin of error of 1. So we pretty much, this is more accurate, the margin of error of 1. So for part B, we actually double the accuracy because we went from an accuracy of 2 to an accuracy of 1 hour. So anytime yeah, it's going down, but the thing is, since we're talking about accuracy, accuracy for margin of error, if it goes down, that means we're getting more accurate. So for this one, technically, it got double the accuracy because we went from 2 to 1. Because versus being within 2, now we're within 1, and now we're doubling the accuracy. So for this one, since we're talking about accuracy, it's actually a good thing if it goes down. It's actually a bad thing if it go up. Because say if I would have said from 1 to 2, that would have been a bad case because that means the two are less accurate. So you kind of have to get it, understand that since a smaller value means that you're more accurate, that's what we're talking about when we say that we double the accuracy. Because 2 to 1, since we went from an accuracy of 2 hours to an accuracy of 1 hour, we technically double the accuracy. All right, so hopefully that answered your question. And let's go ahead and do this one. All right, so here kind of, oh, ooh, here my screen froze. So let's do this. So here's kind of like a little quick recap about this section so that way you can kind of know when to use the Z distribution or when to use the T distribution. So this is when to use the Z distribution. So you use the Z distribution if sigma is known and data is normally distributed or n is greater than 30. When to use the T distribution, you use the T distribution when sigma is not known and the data is normally distributed or n is greater than or equal to 30. So that's when you want to use the Z distribution. That's when you want to use the T distribution. You kind of have to follow those rules. Any question in regard to those rules? All right, so for 7.3, we're going to go over the final section. So this section is going to cover the chi-square distribution. So the chi-square distribution, we use the chi-square distribution where we're trying to do a confidence interval for the population standard deviation. So for this one, you kind of imagine we don't know what the population standard deviation is, but we're trying to figure out what it could be. So for the chi-square distribution, this is the distribution that I told you to go to Canvas. And if you go to the module that says table, where you found the T table, the chi-square table should also be there. Okay, so some quick little notes about chi-square distribution. So the distribution of chi-square is not symmetric. If you actually have the notes, it actually looks like these data set. So if you look at it, these are not normal. So when we have a chi-square distribution, it naturally starts off as skewed to the right. So yes, no, the chi-square distribution is not symmetric. So the second bulletin point said the shape of the chi-square distribution depend on the degree of freedom. Yes, that's the T distribution. So yes, no chi-square distribution. You're also going to have to use the degree of freedom, and degree of freedom is the same formula, is n minus 1. Part 3 said, as the number of degrees of freedom increase, the chi-square distribution become more nearly symmetric. So this is kind of going back to part 1. Part 1 said the chi-square distribution is not symmetric, but that doesn't mean it's always going to not be symmetric. If we have a large enough sample size, that sample size that's large enough will actually become more symmetric. So as the degree of freedom or as your sample size increases, our data set should become more and more symmetric. And the last thing, the chi-square. So the way that you write chi-square is this. So that's chi-square. The chi-square value is never going to be negative. It's always 0 all the way to infinity. So if you look at this starting off point right here, the starting off point will always be 0 and will always go all the way to infinity. Any questions so far about chi-square distribution? All right, so let's get started. So these are going to be the formula. So if you look at it, there are two formula, one for the variance, one for standard deviation. The only thing different from this one to this one is if you look at it, this one has a square root. This one doesn't have a square root. But pretty much they're both of them the same, depending if you want to find variance or standard deviation. Variance, you find it by not taking the square root. If you want to find standard deviation, you have to take the square root of it. And just know that this and this are going to come from the chi-square table. So that's something that you're going to have to find on the chi-square table. The part on top, that's something that you can actually do. Well, that's actually something that will be given to you. All right. Any question in regard to this formula? All right. So let's go ahead and do an example. No. All right. Just ignore that picture. All right, so for this one, it said one way to measure the risk of stock is through the standard deviation rate of return of the stock. The following data represent the weekly rate of return in percent of Microsoft for 15 randomly selected a week. Compute the 90% confidence interval for the variance risk of Microsoft stock. So if you look at it, we want to do the confidence interval for variance. So we're gonna have to find that portion. But before we actually do that, we have to find our sample standard deviation. So this is our sample. And what we have to go ahead and do, we have to go ahead and find the standard deviation of that sample. So if you remember on the TI-84, what you want to do, you want to enter this data set into your list, and then you do a 1-bar stats. If you're doing this in ClassCalc, well, I'll you do it right now in ClassCalc. So let's do this in ClassCalc. So erase, erase, erase. All right, so in ClassCalc, we're going to say stats. We're going to go to right here. If you look where it says ST deviation, so we're going to go over here. So I'm going to enter the number. So we'll say 5.34, comma, 9.63, comma, negative 2.38, comma, 3.45, comma, negative, 8.76, comma, 2.12, comma, negative 1.95, comma, 0.27, comma, 0.15, comma, 5.84, comma, negative 3.90, comma, negative 3.80, comma, 2.85, comma, negative 1.661, comma, and lastly, negative 3.31. And that's it. So if you look at it, it gave me two numbers. It gave me population standard deviation and it gave me sample standard deviation. So for this one, all I care about is sample standard deviation, because since this is a sample, not the entire population, that's why we're using S. So we get 4.69. Everybody get 4.69?
Where did you go on this the class calc? You went to stats and what else?
So you go to stats.
Mhm.
So you go to stats, and then just right here where it says S.
Oh.
Yeah.
Oh,
And then you enter the numbers.
thanks.
Yeah, no problem. All right. Any other questions? All right. So that's all for class calc. Let's see this. All right, so let's go back to my notes. So we want to use this formula. So we want to say n minus 1 s squared divided by chi square of alpha divided by 2. And we want to use n minus 1 s squared of chi square 1 minus alpha divided by 2. So those are the two formulas we want to use. So far I know what S is equal to. S is equal to 4.69. So wherever I see an S, I just need to put 4.69. What I need to find next, I need to find what my N is. So if you look at N, all you have to do is count. So you go, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So N is 15. Lastly, what we want to go ahead and do, we want to say what's the confidence, well, let's do degrees of freedom. And then we'll also do confidence level. So for this one, what's my degrees of freedom? Yeah, 14, perfect. And if you look at my confidence level, we want a 90% confidence interval. So that means we're gonna say 90% here. Yeah. Everybody go for everything so far. I have note data.
Wait, how'd you get the 14 for DF again?
N minus 1, so 15 minus 1.
Oh, all right, thank you.
Yeah, no problem. Okay. Yeah, you have to use both formulas. Okay, so up next, I'm gonna start substituting everything in. So N is equal to 15 minus 1 times S, which is 4.69. You get a square, divided, and this is chi square alpha divided by 2. Right here, you put 15 minus 1, 4.69 square divided by chi square 1 minus alpha divided by 2. So if you kind of notice, everything is given to us. The only thing we don't know is the two numbers that go on the bottom. So in order to find those two numbers that go on the bottom, that's where we're going to use the chi-square table. So for the chi-square table, it's going to be a little bit different because usually for like 7.1, 7.2, all we had to do is find the one value. and it was good for both of them. But for this one, we actually have to find two separate values. So the way that we're gonna find the two separate value is by using the degree of freedom, which we know is 14, and we're gonna use confidence level, which is 90%. All right, so what we first have to go ahead and do, we're gonna first have to go ahead and find what alpha is equal to. So in case you forgot what alpha is equal to, is 1 minus confidence level. And confidence level, you have to put out the decimal. So if I do 1 minus confidence level, I do 1 minus 0.90, which is 0.10. All right. Everybody good so far on how I got alpha is equal to 0.10? All right. So first thing I'm going to do, I'm going to use this formula right here. So if you look, it says chi square alpha divided by 2. So what I'm going to do, I'm going to substitute for alpha. So we're going to say chi square 0.10 divided by 2. So now I'm going to do 0.10 divided by 2. So if you do 0.10 divided by 2, you actually get chi square 0.05. Everybody got how I got 0.05? All right. So I'm going to look for chi-square 0.05 on the chi-square table. So I'm going to go to the chi-square table. I actually don't have it, so give me a minute for I could download it. All right, so here goes the chi-square table. So I'm going to look for chi-square 0.05 on top. So if you look at that, it is right up here. That's 0.05. So I'm going to select this entire column. Any question on why I selected 0.05, pretty much anything in yellow? So if you look at it, I have many, many options to choose from. In order to help me decide which option I want to pick, I have to figure out what my degree of freedom was. So in this case scenario, what was my degree of freedom? So what's my degree of freedom? 14, perfect. So I'm going to select degree of freedom of 14. And that's how you get your chi-square value. So you get 23.685. So it's a 23.685. So instead of putting this number over here, we're going to put 23.685. Cool. Yeah, where it intersects. All right. Everybody good so far? Where the 23.685 come from? Okay, so now we're gonna do the next one. So now I'm gonna do this one. So you say chi square of 1 minus alpha divided by 2 is equal to 1 minus alpha, which is 0.10 divided by 2. Oops, I forgot the chi square. So you get chi square 1 minus alpha divided by 2. If you do 0.10 divided by 2, you get chi square of 1 minus 0.05. If you do 1 minus 0.05, you get chi square of 0.95. So now I'm going to look for 0.95 on the chi-square table. So let me go back to the chi-square table. All right, so now we're going to use this column over here. Because if you look on top, oops, sorry about that. Because if you look on the top, it says 0.950. So if you look at 0.950, and if you look at the degrees of freedom, if you look at where do they intercept at 6.571. So 6.571. So you get 6.571. Any question where that number come from? So instead of putting chi-square 1 minus alpha divided by 2, I'm just going to go ahead and replace all of this with 6.571. And now that I have those two values, now I can actually just go ahead and calculate this on my calculator. But any question on how I got this portion of 15 minus 1 times 4.69 to the second power divided by 23.685, or the other one? All right, so I'm gonna go ahead and calculate this on my calculator. So 14. All right, so if you do the first one, so if you do this one right now, you should get 13. Oh, sorry about that. You should get 13.0. So then if you do the second one, you should get 46. And we'll say 9. And that's how you get the confidence interval for variance. If I wanted to find the confidence interval for standard deviation, all you have to do, you take the square root of 13.0 and take the square root of 46.9. And that will give you the confidence interval for the standard deviation. So variance just means you don't take the square root. But if you want to find the confidence interval for standard deviation, you have to take the square root. All right, but that's it for that first problem. Any question in regard to that first problem? All right, so let's do this last one and then that's it for today. So it says Coca-Cola is worried that their machine are getting too old and they are not consistent. They randomly select 15 bottle of Coca-Cola and got a mean of 16.95 ounces with a standard deviation of 0.67 ounces. Assume the population is normally distributed. So for part A, it says constructing 95% confidence interval for the population standard deviation. So if you look at it, they tell us we have a sample size of 15. They tell us we have a standard deviation of 0.67. They tell us we have a mean of 16.95, but that information is useless to us because we're trying to do the confidence interval of a standard deviation. We don't care about the mean for a confidence interval of standard deviation. All right, everybody good? So N is 15, S is 0.67. Okay, so if you look at part A, it says constructing 95% confidence interval for the population standard deviation. So this one, we want to construct it for the confidence interval standard deviation. So this one, you do take the square root. So you say n minus 1 times s squared, all divided by chi-square of alpha divided by 2. And you also want to get a square root of n minus 1 s squared, all divided by chi-square 1 minus alpha divided by 2. All right, so just remember, if I want to find the confidence interval of variance, you don't need the square root, but if you want to find the confidence interval for standard deviation, you do have to take the square root of your answer. All right. Any question for the formula so far? Okay, so I'm gonna go ahead and just pretty much start filling out everything that we do know. So I know what n is. N is 15, so I'm gonna do 15 minus 1. I know what standard deviation is. That's 0.67. Same thing for over here. I know what n is. N is 15. Standard deviation is 0.67. So far, everybody good with those substitution? All right, so up next, what I'm gonna go ahead and do, find the chi-square value. So for the chi-square, you first have to find alpha. So to find alpha, alpha is 1 minus confidence level. In this case, confidence level is 95%. So you put 0.95, which is 0.05. All right. Any question? I got alpha is equal to 0.05. All right. So right now I'm gonna go ahead and find this value over here. So we're gonna find portion. So I'm gonna go ahead and find chi-square of alpha divided by 2, which is just chi-square 0.05 divided by 2, which would give me chi-square 0.025. Okay, if you do 0.05 divided by 2, it should give you 0.025. Any question on how I got chi-square of 0.025? All right then. So now what I'm going to go ahead and do, I'm going to go ahead and look for this on the chi-square table. So let's look for in chi-square table. Chi, where are you? Oh, partial. Oh, please. All right, so if you look at, we're looking for 0.025. So 0.025 all of this. If you look at it, we're looking for degrees of freedom. I believe it should have been 14. So degree of 14 is right over here. So if you look at the value that we got, you get 26.119. So that's going to be our chi-square of alpha divided by 2, 26.119. Any question in regard to 26.119 or how did we find 26.119? So 26.119. All right, so we found 26.119. So that means for here, I'm going to erase this, and we're going to put 26.119. Up next, what I want to go ahead and do, I want to find chi-square of 1 minus alpha divided by 2. So if we're looking for chi-square of 1 minus alpha divided by 2, that's pretty much equal to chi-square 1 minus 0.025. And if you do chi-square of 1 minus 0.025, that should give you 0.975. So right now we want to look for chi-square of 0.975. And we also want to look for degrees of freedom of 14. Any question on how I got chi-square of 0.975? All right, so let me go ahead and look for chi-square. So we're looking for chi-square of 0.975. That's all here. if you look at where do I intercept it, it intercepts at 5.629. 5.629. So right here, you put 5.629. Any questions so far? I got the 5.629 for that one. All right, so I'm gonna go ahead and just solve this in my calculator. You could do so on your TI-84 or ClassCalc, and you should get the same answer that I get. Also, in case you've been wondering about, is there a way to do this in the calculator? For this one, there actually is no way to do it in the calculator, where the calculator will give everything for you. So you do kind of want to know how to do everything, because the calculator is not going to save you for this one. So that's our confidence interval for the standard deviation. So the confidence interval for the standard deviation could be anywhere between 0.49 all the way to 1.06. Any question in regard to how I found the confidence interval? All right, so the last step is, how can I use this confidence interval? So if you want to stay after class, or just stay after, and I'll show you how to enter into the calculator. So what you want to do, you kind of want to be able to interpret this. So you kind of just have to remember, what is standard deviation? Standard deviation is kind of just telling us how consistent something is. So kind of think about it, something that has low standard deviation mean it's really consistent. Something that have a huge standard deviation is something that's not consistent. So usually when we're looking for standard deviation, you want standard deviation to be a low number. Because if you get standard deviation to be a high number, there might be something wrong, because it's telling you that it's not consistent. So if you look at it, we get that it could be anywhere from 0.49 all the way to 1.06. So B is asking, if the standard deviation is 1 ounce, Coca-Cola need, so if the standard deviation is 1 ounce, Coca-Cola need to replace all the machine. Looking at part B, looking at part A, confidence interval, should they consider replacing all of their machine? Explain why or why not. So Coca-Cola is saying, if the standard deviation is 1 ounce or higher than 1 ounce, they need to replace all of the machine, because it's kind of telling us the machine are not working. If the standard deviation is below 1 ounce, then it's telling us the machine are all working as normal. So in this case, should they replace the machine, or should they keep all the machine? Well, for this one, you kind of want to be careful, because it's saying if it's 1 ounce, they need to replace all of the machine. Oh, sorry, I stopped sharing for some reason. So this is So for this one, they're actually telling us, if the machine is 1 ounce, or the standard deviation of that machine is 1 ounce or more, it's telling us we need to replace all of the machine. So in this case, if you look at 1 ounce, you go, does 1 ounce fall in between here? If it falls in between here, it's telling us that it is likely that 1 ounce could be the standard deviation. If it falls outside of this range, it's telling us it's not possible. So if you look at 1 ounce, since 1 ounce is between 0.49 and 1.06, it's telling us that it is possible that the machine have a standard deviation of 1 ounce or more. So for this one, we want to say you should replace all the machine. Because if Coca-Cola is saying that if the standard deviation is higher than 1 ounce, they need to replace all of the machine. This confidence interval is telling us that it is possible that the standard deviation is 1 ounce or higher than 1 ounce. So that way for this one, we'll say replace all the machine. All right, and that's it. Any question for that last problem?